Hello there, and welcome to the Chapter 10 lecture for Chemistry, CHE 102, second semester. So we're starting this semester at Chapter 10. And Chapter 10 is all about liquids and solids. Actually, it's really just an introduction to liquids and solids, mainly the types of forces that hold them together, and a little bit of the energetics about phase changes. So before we dive in, I do just want to refresh your memory a little bit about polarity and electronegativity because it's really important in understanding the intermolecular forces that we're going to be talking about. And so if you're rusty, you'll have trouble following along. So we're just going to do a quick refresher. All right, so let's see. Let's change up my pen color here. I like purple. We're going to go with purple. Purple. All right. So this concept of polarity has everything to do with something called electronegativity. And sometimes, since it's a long word, I just abbreviate it as EN, electronegativity. All right, so electronegativity is a somewhat arbitrary value that measures the strength of an atom's pull on electrons in a shared bond. So when two atoms are sharing electrons in a covalent bonding situation, one of them, they just don't usually share equally. One of them will oftentimes hog electrons. So if we look at the periodic table here, we can see that the electronegativity increases as we go right and up the periodic table. So it increases up and to the right. All right, with the exception being these guys here, the noble gases, because the noble gases don't bond. So they don't have a pull on electrons in a bond because they don't tend to share electrons at all. They're pretty greedy and keep theirs all to themselves. So the four biggest electron hogs on the periodic table are these guys right here. And when other elements bond with them, and they're fluorine, oxygen, nitrogen, and chlorine, or as I like to say, phone call, they have a tendency to hog electrons and sort of have majority custody of them. So in a covalent bond situation, whatever element has the higher electronegativity will have the stronger pull on electrons, which results in partial charges. And we indicate those with the Greek letter delta, so you can have a partial positive or a partial negative charge. So an example that I have here is hydrogen bonded to chlorine, HCl, hydrochloric acid. So hydrogen, if we wrote out their electronegativities, if we look at this table up here, hydrogen has an electronegativity of 2.1, chlorine has an electronegativity of 3. So chlorine's is greater than hydrogen. So the electrons basically are going to be hogged in this direction. Right? And we can draw this arrow, it's actually a vector, put a little plus there, that shows the direction of electron pull. We call this the dipole moment, is what this is called. And all it is an arrow that shows the direction electrons are being hogged towards. Right? We can also indicate the partial charges that each of these atoms will sustain. So the chlorine is hogging electrons, so electrons are negatively charged. The chlorine is going to be partially negative, and that hydrogen is going to end up being partially positive. So we call these partial charges. And this is so this molecule, we would call this a polar molecule. Those charges result in poles, oppositely charged regions. And so we say that a molecule that has poles is a polar molecule. So molecules can be either nonpolar or polar. Nonpolar or polar. So a nonpolar covalent bond and a nonpolar covalent compound, they don't have poles, so they don't have unequal sharing, which means that they do have roughly equal sharing of their electrons. So if two atoms have similar electronegativities, so they're within about 0.5 of each other, this results in relatively equal sharing, and so you end up with no partial charges. So some examples, all right, two atoms that are going to always share equally are going to be two atoms of the same element. So for example, a hydrogen molecule, HH, or a fluorine molecule. All right, if I draw the Lewis structure here of each of those, all right, they're going to share really equally. They have the same electronegativities. They have the same pull. All right, here's another example. This is an example of a molecule that has polar bonds, but is not polar itself. So CF4, get all my lone pairs in here. All right, so while these bonds themselves are polar, fluorine is an electron hog. It's going to pull electrons away from that carbon. Okay, I'm just going to draw all these dipole moments. All right, but notice that all the dipole moments are going in equal strengths and opposite directions, so they essentially cancel each other out. Another way to think about it is that all ends of the molecule are sort of negatively charged. So when you have that kind of symmetry in a symmetrical molecule, the fact that there are polar bonds, the whole molecule itself ends up being nonpolar. Another classic example is, I want my purple back, carbon dioxide. So CO, O. All right, there's the structure. So oxygen isn't a big electron hog. Carbon is not. So oxygen's going to pull electrons, but they're pulling equally in opposite directions, so they basically cancel out. So these molecules, even though they contain polar bonds, all right, are nonpolar overall. They're nonpolar molecules because of their symmetry. That symmetry causes those poles to be the same and not opposite. Okay, so polar molecules, by definition, have poles. And that is caused by the unequal sharing of electrons. And this happens when there's a difference in electronegativity, that's the delta symbol means difference, of between approximately 0.5 and 1.8. This is somewhat arbitrary, somewhat approximate. So I typically discourage students from trying to do the math using this table up here. It's more about understanding that any one of these four is really going to be a big hog when it's paired with something else. Okay, so my examples here. Let's see, let's do H2S. And I just told you, I really don't expect you to know those big four hogs, and then here I give you one without one of the hogs. All right, sulfur is a significant, well, let's see, sulfur and hydrogen, actually they're pretty close together. Sulfur is an electronegativity of 2.5 and hydrogen has an electronegativity of 2.1. So this one happens to be polar because experimentally that's what we have found. But I guess if we're working with the math rule, we would classify it as nonpolar. Yikes! That was an alarm. So scratch that. Literally, we're going to scratch that out. And we're going to do a different example. Let's do hydrogen fluoride or hydrofluoric acid. All right. Hydrogen, not a hog. Fluorine is. So draw our dipole moment here. Our fluorine is going to be partially negatively charged, and because it's got a lot of electrons around it, and the hydrogen is going to be partially positive charged. Some other examples, we've got, how about this molecule, and this one here. All right, so I'm going to start with the second one that I've drawn. So the second one here has one polar bond, this one right here, the CF bond. All right, C and H have very similar electronegativities, and they share pretty equally. So the only polar bond here is that fluorine, which means that fluorine is going to be partially negative, and the rest of the molecule, namely the carbon, will be partially positive. And then this one that I've drawn here, oxygen is our hog. It's going to hog electrons and end up with a partial negative charge, and the rest of the molecule will end up with a partial positive charge. Okay? So what we're going to see in this chapter is that even though these charges are partial, all right, they are still, they still attract. Opposites attract, whether they're full opposites or partial opposites. And that's really going to be the theme of this chapter. So the third type of bond, we talked about the two types of covalent molecules and covalent compounds, nonpolar and polar, but there are also ionic bonds. And in chemistry, we often we talk about the two types of bonding. There's covalent and there's ionic, as if there's two different discrete types. But technically, it's really a spectrum of bonding. And I don't know, when I first learned this, it kind of blew my mind because it kind of connected everything. But in ionic bonds, you have atoms that have a large electronegativity difference, so large that the stronger one, the hog, literally takes the electrons from the other. And so ionic bonds involve transfer of electrons, and they form ions, which have full charges, a legit positive or negative charge. So if we look at this spectrum here, a nonpolar covalent bond, or sometimes called a pure covalent bond, like two atoms maybe of the same thing. So let's say two atoms of fluorine. Okay, they're both hogs, but they equally hog electrons. So the electrons are shared. That little gold zone is sort of like, imagine the electron clouds, and they've kind of fused together here. So they're sharing electrons. The electrons are spinning equal time around each. Okay, but as we go down the scale and electronegativity values become more and more different, so now we have fluorine and hydrogen. All right, now the fluorine has a stronger pull on the electrons. It hogs the electrons around it, so its cloud is bigger, and it has a partially negative charge, and the hydrogen's cloud is smaller and has a partial positive charge. I like to think of it as kind of like, you know, my parents are divorced and they had shared custody, but my mom had us most of the time, and my dad, we were just there every other weekend. So it's kind of like a covalent bond is kind of like co-parenting or like custody, shared custody, which is not necessarily 50-50. And then as we move down this spectrum even more, as that electronegativity difference gets greater and greater, we get to a point where one atom has such a strong pull on electrons that it just freaking rips the electrons away from the other one. So let's say this is fluorine and this is sodium. All right, and that sodium, metals have very low electronegativity values. So when it gets close to fluorine, fluorine just rips that electron right out, and then it has a full extra electron and a full negative charge, and the sodium is missing an electron, so it ends up with a positive charge. Okay, so these bonds that we're talking about, covalent and ionic bonds, these are what we call intramolecular forces. All right, intra means within. These are forces between atoms within the molecules, and we draw these as solid lines. All right, so HF, that's a covalent bond. It's a force. It represents the sharing of electrons, right? But there are also things called intermolecular forces. So if we have two molecules of HF, okay, they are actually attracted to each other. The HF, the fluorine is partially negative, the hydrogen is partially positive. All right, and these partial charged ends, these poles, actually attract each other because opposites attract. But we draw those as dotted lines. My dotted line's a little sloppy there. But intermolecular forces are attractions, and since they're not as strong as intramolecular bonds, ionic and covalent bonds, we don't draw them as solid lines. We draw them as dotted lines to distinguish them. So the real example I wanted to do was two water molecules. So H2O, H2O, okay? So the blue lines here, all right, represent the intramolecular forces, covalent bonds that hold them together. But because the oxygen is an electron hog and has a high electronegativity, it's going to hog the electrons and have a partially negative charge, and the hydrogens will have a partial positive charge. Okay, and so what happens is they're attracted to each other. The hydrogen of one is attracted to the oxygen of another, and likewise, this hydrogen could be attracted to that oxygen. Okay, so those opposite charges, those opposite partial charges attract, and those are intermolecular forces. Okay, so there's several types of intermolecular forces, which I will abbreviate heretofore as IMF, intramolecular force. Another synonym is they're sometimes just called attractive forces. Different textbooks, different like YouTubers, different chemistry teachers will have a different preferential term. One of my peeves with chemistry, throughout chemistry, is like lots of synonyms, lots of alternative terms to keep track of. So intermolecular forces, aka attractive forces, aka IMF. All right, so whenever we have attractive forces between neutral atoms or neutral molecules, like water, like HF, all right, these are technically called van der Waals attractions. Van der Waals attractions. So the three types of van der Waals attractions, starting from weakest to strongest, is what this arrow represents. All right, so the weakest force is they're called London dispersion forces. All right, and the London is not referring to the city, it's actually referring to the last name of the scientist who first described them. Sometimes they're called London forces, sometimes they're just called dispersion forces, and sometimes they're called London dispersion forces, and sometimes people just refer to them and call them van der Waals forces, but really they're just one type of van der Waals force. Another type of van der Waals force are dipole-dipole interactions. And the third type is hydrogen bonding. Hydrogen bonding. All right. There are also attractive forces that exist between ions. Of course, there is ionic bonding, which we already sort of discussed. That's when you have a full positive and a full negative attracting each other. But another one that you can have is something called an Ion-Dipole Attraction. So that's when you have an ion, something that's fully charged, that's attracted to a polar molecule that has a partial charge. So These are the 5 different types of intermolecular forces that 2 molecules can have with each other. And we're going to go through each of these in more detail now. So starting with the London dispersion forces, which are kind of the most complicated, I think, to understand, but also the easiest in the sense that every molecule has them. So London dispersion forces are in all molecules, okay? But it's the only attractive force that exists in nonpolar molecules. So what is a London dispersion force? So London dispersion forces, they're due to temporary dipoles that form when electrons are flying around. Okay, so imagine you have an atom, you have 2 atoms that are next to each other, all right, and their electrons are just spinning around here in the cloud. And then a split second later, in atom B, 2 of those electrons, they're flying around, end up being localized to one side of the atom. All right, and when that happens, it makes the atom a little bit polar, right? And so when that happens, that's what you can see in this picture here, so the atom becomes a little bit polarized. And then that polarization of this atom, this negative, partial negative charge, the electrons here, end up repelling the electrons in atom A and inducing a dipole in atom A. Okay, so even in nonpolar atoms that don't have dipoles, their electrons are always moving. They're flying around in that electron cloud. And so it's very reasonable and probable and actual that occasionally, for a split second here and there, the electrons are localized to one side, which causes it to become polar for a second, and that pole induces poles in neighboring atoms or molecules. Okay, so then just as quickly as it formed, it unforms, the electrons, keep flying around, and then we go back to this state over here. So these dipoles are very temporary, but while they exist, they do exert an attraction. So London dispersion forces are very weak, but they can be additive and become very significant. So things that influence the strength of London dispersion forces are A, the size of the molecule and the shape. So the larger the molecule is, the more electrons it has, and therefore the more polarized it can become. The more electrons can shift. And so by definition, as the molar mass goes up, the London dispersion forces go up. Okay? So if you have 2 molecules and they are different sizes there, but let's so down here, if we had pentane right here versus methane, all right? So methane is going to have much lower London dispersion forces than pentane because pentane is just a larger molecule. Another thing that affects it is the shape of the molecule. So in order for these dipoles to be induced and for their attractions to exist, atoms need to be able to be relatively close to one another, come in close contact with another. If a molecule has a whole bunch of funky branches, okay, then those molecules are not going to be able to pack real tightly together and have a lot of surface contact. I like these space-filling models here. So pentane, isopentane, and neopentane, they're all isomers. They have the same molecular formula of C5H12. So they all have the same molar mass. They're the same size, technically, but they're different shapes. And as you can see here, pentane has the longest shape, and so 2 pentane molecules have quite a large amount of shared surface connection. Whereas neopentane here is in a 3D view, space-filling model, it's almost like a ball. And so when you put them close together, there's a very small amount of contact area. So they will have the weakest London forces. So in terms of London forces, pentanes is greater than isopentanes, which is greater than neopentanes, which is greater than methanes. Okay, so London forces in large molecules are pretty significant. And I'll get to that in a few minutes. Okay, dipole-dipole forces, the second type of van der Waals attraction. And these are found in all polar molecules, and these are due to permanent dipoles. So molecules that permanently have a partially positive and partially negative area. So here's an example that I have here where here's the structural formula. So it's CH3OCH3. This would be dimethyl ether. And here's the space filling model version. And so we can see that there's an oxygen here. Oxygen, being an electron hog, is going to be partially negative, leaving the back end of the molecule partially positive. And this is called an electrostatic potential map. It's sort of like a heat map that shows you that sort of the cloudy area represents the electron cloud, and red areas represent a high density of electrons, and blue represent a low density of electrons. So you can see it's very hot here. This represents the partially negative electron packed zone versus the partially positive electron poor zone. And so these poles, if you will, these molecular poles, attract each other. And so polar molecules are typically more strongly attracted to each other than nonpolar molecules. Granted, it depends on a lot of factors like size and the strength of the dipole moment. So different atoms have different electronegativities, and so the size of that dipole moment or the strength of their pole is going to be different. So if we look at the halogens, the halides here, HF, HCl, HBr, and HI, these are all group 7 halogen elements. And if I just draw a little clipping here of the periodic table, all right, fluorine, chlorine, bromine, iodine, we know electronegativity goes up, or it goes down as you go down the periodic table and up as you go up the periodic table, with fluorine being the biggest electron hog. Okay, so HF bond is going to be more polar than the HI bond. Even though iodine is a larger atom here, that's why the size is different of those colored balls, because the atoms are getting larger, but the electronegativity difference is getting smaller and smaller. And so 2 HF molecules are going to be more strongly attracted to each other than 2 HI molecules, simply because the dipole moment is greater, those partial charges are greater. All right, the third type of van der Waals attraction is hydrogen bonding. And I put quotes here because it can be confusing when we call it a hydrogen bond, because then we want to sort of categorize it with covalent bonds and ionic bonds, and it's not really a true bond, it's a type of attractive force. Though I guess you could say no bond is a true bond, they're all some kind of attractive force. And actually a paper just came out recently that said hydrogen bonding is actually, like, I don't know, on a physics level really close to covalent bonding. So maybe I can stop using these quotation marks that I like to use. But anyway, just remember that a hydrogen bond is a type of intermolecular force. It's not an intramolecular force, so don't get it confused with the intramolecular forces of covalent and ionic bonding. Really what hydrogen bonding is an extra strong dipole-dipole force. So it's just happens when we have two polar molecules, but specifically they are polar molecules that have an hydrogen bonded to a fluorine, oxygen, or nitrogen, the top 3 electron hogs. Because when the hydrogen is bonded to one of these 3 guys, its partial positive charge is particularly large. There's a large dipole moment here, okay? And so when it comes into contact with another fluorine, oxygen, or nitrogen on another molecule, these guys have particularly large partial negative charges because they are the top 3 electron hogs. And so it ends up in this particularly strong dipole-dipole attraction. I'm just going to do a little like this. Okay, my red dotted lines to represent hydrogen bonding. So we can call these guys, any molecule that has an F, O, or N bonded to an H is a hydrogen bond donor. H bond donor. And any molecule that has an electron hog, F, O, or N, whether it's bonded to an H or not, is a hydrogen bond acceptor. All right, the key thing to remember here, the biggest mistake people make with hydrogen bonding is this. All right, CH bond. This is a nonpolar bond, okay? Carbon-hydrogen bonds do not result in hydrogen bonding. So if we look at this picture over here, I have 2 molecules of methanol, and I'm going to draw some hydrogen bonds between them. So first, I'm going to indicate my partial charges. So carbon-hydrogen bonds are not polar, so there's no partial charges there. But oxygen has a strong pull, so it's going to be partially negative, and it's going to make that hydrogen particularly partially positive. Okay, so in this scenario, we can have attraction here between the hydrogen of one and the oxygen of the other. Okay, this molecule happens to have a hydrogen bond donor and a hydrogen bond acceptor. So if you have a bunch of these methanol molecules, they will hydrogen bond with each other. Okay, sometimes though you have a molecule that has a hydrogen bond acceptor but does not have a hydrogen bond donor. And that example is here in this practice problem. So I've got a carbon-hydrogen bond that is not polar, and I have a carbon-nitrogen bond that is polar. Nitrogen is has a high electronegativity, and carbon does not. So we do get these, HCN is a polar molecule. Okay, water is polar as well. Oxygen hogs the electrons from the hydrogens. Oxygen hogs electrons from hydrogens. Okay, so these water molecules, hydrogen bonds are typically drawn as red dotted lines in textbooks. So these water molecules can have a hydrogen bond like that, or there could be a hydrogen bond like that. All right, so the oxygen and hydrogens on the opposite molecules can attract each other. So water molecules can hydrogen bond with each other, okay? There are no hydrogen bonds between the HCN molecules because there is this hydrogen here, but it is not polarized, okay? So there is no hydrogen bonding between these 2 molecules of HCN. If you had a test tube full of HCN, there would be no hydrogen bonding in that test tube. But if you added water to it and you mixed them together, all right, you would have hydrogen bonding because the water molecule has a partially positive hydrogen, that is the hydrogen donor, all right, and it will be attracted to that negative nitrogen on the HCN molecule. So you can have hydrogen bonding between 2 molecules of the same kind, and you can have hydrogen bonding between molecules, different types of molecules. And there are some types of molecules that don't have the ability to hydrogen bond with themselves because they don't have a hydrogen bond donor, all right, but they can hydrogen bond with other things because they have a hydrogen bond acceptor, an F, O, or N. So there might be some practice problems in the homework that have you do some stuff with hydrogen bonding or drawing hydrogen bonds. So being able to do that is important. It's very important in biochemistry and organic chemistry. So if you're moving on in chemistry, this concept of polarity and hydrogen bonding, super, super important. So the strength of hydrogen bonds, all right, is going to depend on a couple of things. For one, it will depend on the size of the dipole moment, just like we saw before with polarity. A stronger dipole moment ends up with larger poles, or more partially charged, a larger partial charge, which ends up in greater attraction. Also, the number of hydrogen bonds that are possible. So, for example, if I draw out that methanol molecule again, just draw it like this. All right, versus water. Guess I'll get my lone pairs in there, okay? So, methanol has one hydrogen bond donor. This hydrogen here can hydrogen bond because it's attached to an oxygen. All right, these hydrogens cannot. They're attached to a carbon. They are not partially positively charged. This oxygen can also engage in hydrogen bonds. So technically it can engage in two. It has two hydrogen bonding sites. So this one could have a total of 3 hydrogen bonds. And the water molecule over here has 2 hydrogens that could engage in hydrogen bonding. And this oxygen, which also has 2 potential hydrogen bonding sites. So water can have 4 hydrogen bonds, all right? So the hydrogen bonding in water molecules is stronger than the hydrogen bonding in methanol molecules because there's just more of it. So those are the 3 types of van der Waals attractions, the types of attractions you get between non-charged neutral molecules or atoms. All right, but we can also have another type, an attraction between non-charged and charged substances. So when we have ions and polar molecules, they will actually engage in intermolecular forces because one has a full charge, the other has a partial charge. They're still charges, they're still opposites, and they still attract. So the classic example is when we dissolve sodium chloride, salt, in water. So sodium chloride is in a crystal structure. It looks something like this, where it's just a bunch of ions just stacked together. And when we add it to water, and here's our polar water molecules with the little negative sign on the oxygen and the positive signs on the water. Right, when we mix them together, what happens is the water molecules surround the ions. Notice here, all right, we've got our positive cation in the middle here, and notice all the water molecules around it have their oxygens, their negative side facing this positive ion. But then if we look here at the negative ion, the chloride ion, the water molecules are inverted. They're flipped the other way such that their hydrogens, the positively charged hydrogens, are attracted to that ion. So these attractions are called Ion-Dipole Attractions. So they're kind of a little bit like, hydrogen bonding, but just stronger because it's not between 2 partial charges, it's between a partial charge and a full charge. So the strength of ion-dipole forces are going to be due to the magnitude of the ion charge. So, chlorine has a 1 negative charge, but oxygen has a 2 minus charge. All right, aluminum has a 3 plus charge. So the larger the magnitude, the number of the charge, the bigger the attraction will be. And then, of course, with the polar molecule, the larger the dipole moment, the greater the attraction will be. So those are all of the different types of attractive forces, the 4 different types. I didn't go into ionic bonding because that was several chapters ago. This is a nice summary table of the different attractive forces that are really useful when you're reviewing or like if you are doing homework problems and you just need like a little cheat sheet to refer to, all right, to help keep them straight. This is a really helpful table, so I threw it in there. Okay, so now that you know what all these different intermolecular forces are, now we'll talk about why they matter. And they matter because they, like, no pun intended, determine a lot of the physical properties of the matter around us, including their state. So solids are solid because the molecules pack together tightly and have a lot of intermolecular forces holding them together in that packed shape. In a liquid, you have weaker intermolecular forces, so some atoms or molecules are close enough to have attractive forces, but they are somewhat weaker than in that solid state. And then lastly, in the gaseous phase, the molecules or atoms are bouncing around so fast that they're not engaging in any intermolecular forces because they're just moving too quickly. So as we increase temperature, we increase the kinetic energy and the speed of these atoms and molecules, which disrupts the intermolecular forces and essentially sets them free. So as we move right here, we're increasing the temperature and increasing the speed and kinetic energy. But as we go left here, solids have more intermolecular forces than gases do. So some of the that's not a word, some of the characteristics of matter in their different states. So in a liquids have a boiling point. That is the temperature at which they go from a liquid to a gas. And the stronger the attractive forces are, the higher the boiling point and melting point, since melting is this way. All right. The higher the intermolecular forces, the higher the boiling point and melting point will be. Because if you think about it, in order to go from a solid to a liquid or a liquid to a gas, you have to provide enough energy to disrupt those attractive forces. I like to think of all these molecules as like holding hands. And if you it's kind of like Red Rover. If you ever played that game, you have a whole bunch of people standing in a line and you send someone running over. And if they run over with enough energy, they break your hands apart and they break through. So when you heat up a liquid, if those molecules are moving and vibrating enough that they have to let go of each other's hands, then you have a gas. So if we look at some trends here are a list of alkanes of hydrocarbons that are just made of carbons and hydrogens. And here's their boiling points. So methane, which is the smallest hydrocarbon, has a very low boiling point of negative 161 degrees Celsius. So methane at room temperature is well above its boiling point, which is why methane is a gas at room temperature. So all of these that have a boiling point at or below room temperature, we'll say all of these guys, all right, these are all gases at room temperature because their boiling points are very low. That's because these are nonpolar molecules. They're all carbons and hydrogens. So the only force they have that holds them together, the only intermolecular force they have, are London dispersion forces. All right, and London dispersion forces are very weak, especially in small molecules. But we know that London dispersion forces are additive, and the more atoms you have, the greater those London dispersion forces are, which is why we see these boiling points trending upward, because as their molar mass gets larger, their London forces get stronger and their boiling points get higher. So that's why octane, the gas you put in your car, is a liquid, while propane, the gas that comes out of your stove, is a gas. Another comparison that I have here, we're looking at an alkane or a hydrocarbon, carbons and hydrogens only, versus a molecule that has an oxygen in it. Okay, so methanol versus ethane. They have similar molar masses, okay, similar molecular weight, so they're about the same size, so their London forces are equal. Okay? But they have different boiling points, and that's because of the fact that this molecule here with that OH, okay, has hydrogen bonding. So while they both have London forces, equal London forces, the second one only has London forces, whereas the first one has London forces and hydrogen bonding. And hydrogen bonding is a much stronger type of attractive force, and that's why it requires much more energy in order to make it transition from phase to phase. So you see that trend with all of these examples here. We just get larger and larger molecules, but we're always comparing a pair that have very similar molecular weights, but very different boiling points, and that's due to the presence of a stronger type of intermolecular force, hydrogen bonding. Another feature of matter that's determined by intermolecular forces is viscosity. So viscosity is, you can think of it as like the thickness of a liquid. It's really the measure of the resistance to flow. And again, the stronger the attractive forces, the higher the viscosity. So something with high viscosity is very thick. Like honey has an incredibly high viscosity. Water has a pretty low viscosity. Other things that determine viscosity are the size of the molecule and its shape. Some molecules that have lots of branches, as they flow, because when something is in a liquid, the molecules are just kind of like rolling around and flowing all over each other. So if a molecule is like long and like has lots of spikes on it, okay, then those molecules have a tendency to tangle. That's going to increase the viscosity. So it's not totally about attractive forces. Temperature, though, does affect viscosity, again, having to do with attractive forces. So if you take honey and you put it in the microwave or you heat it up, all right, it gets a lot less viscous. It gets more runny or thinner. Okay, as we increase the temperature, we decrease viscosity. And that's again because when we increase the temperature, we're decreasing IMF. We're also decreasing intermolecular forces, which will therefore decrease viscosity. Something that's sort of similar and related to viscosity is surface tension. So surface tension is a characteristic of liquids where, so if you have a drop of water, for example, and you put it on a countertop, all right, it doesn't spread out flat, all right? Water tends to form round droplets, dome-shaped droplets, and that's due to the cohesive attractive forces between the water molecules. So this is a picture, I know it's kind of small, but each of these blue balls represents a water molecule, all right? And the green arrows represent attractive forces. In water, the attractive force is hydrogen bonding that holds those molecules together. And so they would rather bunch up together in this dome shape. That's sort of the most energetically favorable shape rather than spread out flat where they would have fewer interactions and fewer neighbors. So they want to have as many neighbors, as many interactions as possible. So surface tension is why water forms round droplets. It's also why a paper clip can float on water and certain water bugs can walk on water surfaces, because at the surface of water in particular, those attractive forces are particularly tight. Okay, and then lastly, another thing that intermolecular forces play a role in is capillary action, which is related to surface tension. So its capillary action is the ability of a liquid to sort of spontaneously move up a tube without, a vacuum or sucking it. And it's due to two types of forces: cohesive forces, which we saw with surface tension. So cohesive means they stick to each other. Okay, like so the water molecules attract other water molecules. And adhesive forces, meaning that they stick to other things. So in the case of water, all right, water molecules are attracted to each other, but they're also attracted to glass to some extent. And so if you put a glass tube in water, the water will move up the glass tube. The thinner the tube, the higher the water goes. And water also forms a meniscus that is a concave shape. Okay, because the water here on the side, like that, that's basically the water hugging the glass. Water is attracted to the glass, so the water that's up against the wall of the glass actually climbs up a little bit. And so you get that concave meniscus shape. That's the adhesive forces at work. Mercury, on the other hand, mercury and glass are not adhesive substances. So mercury, when it forms a meniscus, it actually forms a convex meniscus because the attractive forces between the mercury molecules is strong and there is no attractive force to the glass. So they will basically form, kind of like a droplet does on a surface, whereas the water molecules are attracted to the glass and will actually climb up the side of the glass a little bit. So the identity of the material is important. Other things like the density of the liquid, the width of the tube, also change the capillary action. The textbook goes into how to mathematically calculate some of the capillary action stuff, but we're not going to get into that. I just want you to know the role that intermolecular forces play in those different characteristics. Now we're going to take a little side boondoggle off to thermochemistry a little bit and talk about the energetics or the energy transfer that occurs during state changes. So I like this diagram here. It's a really nice diagram showing you the different changes, what they're called. So going from solid to liquid is melting, and that is an endothermic process. It has a positive delta H. All right, and so on and so forth. So all of the names of those processes and whether they're endothermic or exothermic, this little reminder diagram up here for you. So let's first talk about this one here. Boiling, evaporation, or vaporization is another word. All right, it's the process by which we add thermal energy to a liquid in order to overcome the intermolecular forces in that liquid and have the molecules become gaseous. All right, it's an endothermic process. Endothermic means it absorbs heat. Endothermic processes have a positive enthalpy, a positive change in heat. All right, the opposite of vaporization is condensation. So condensation is going to be exothermic. All right, so the enthalpy of a vaporization reaction is, we just call it the heat of vaporization or the enthalpy of the vaporization reaction. It's a physical change, but we can still write a chemical equation indicating liquid water going to gaseous water. So that vaporization process, the enthalpy of this, so for 1 mole of water to become 1 mole of gas, it requires 44.01 kilojoules. And to do the opposite, condensation, since it's the opposite reaction, remember if we flip a reaction, we change the sign of the delta H. And so the heat of condensation is the same as the heat of vaporization except with the opposite sign. Okay. Vaporization is a dynamic equilibrium. All right. So in a closed container, if you have a container of water and it's closed, like a bottle of water, all right, some of those water molecules are actually going into the gas state and some are coming back down into the liquid state. Sort of simultaneously, those things are happening. All right, so when we have vaporization, well, no, not vaporization. Well, when we have a closed container, all right, of at any temperature, whatever the temperature is, and it's closed, okay, some molecules will leave and enter this gaseous space, but some of those gas molecules will collide together and reestablish intermolecular forces and come back down into the liquid state. And so when we have that, we can measure the vapor pressure here. All right, so the vapor pressure is the pressure of the gas after this dynamic equilibrium is established. It's dynamic because it's not like, oh, you've finally reached the maximum amount of gas that'll fit in that space and no more gas fits there. It's not that. It's not that molecules stop going into the gaseous state. It's that they're going into the gas and coming back into the liquid at the same rate. Equilibrium, which we're going to do more of this semester, the definition of equilibrium is equal rates. Okay, so it's not that there's equal amounts of gas and liquid, it's that the rate of vaporization is equal to the rate of condensation. So sort of like a little introduction to the concept of equilibrium here. So we can use these thermodynamic values, the enthalpy values, to calculate how much energy is required to boil some amount of water or condense some amount of water. So let's do a practice problem. How much heat is required to evaporate 1.5 kilograms of water at 37 degrees Celsius if the heat of vaporization is 43.46 kilojoules per mole at 37 degrees Celsius? Okay, so the temperature here is a little bit extra information. I stole this from a problem where it was talking about sweat evaporating. So 37 degrees is our body temperature. The enthalpy is dependent on temperature. So notice that up here, the enthalpy of vaporization was 44.01. And in this problem, it's saying it's 43.46 because this was at standard temperature, 25 degrees Celsius. All right, and this is what it is at 37 degrees Celsius. So we don't really care about that temperature per se as long as they match. What we care about is that we have 1.5 kilograms of water, and the heat of vaporization is 43.46 kilojoules per mole. And we want to know how many kilojoules. We want to know how much heat. Okay, so we have kilograms, kilojoules, and moles. Nothing there stands out to me as being able to cancel out. All right, but water, I know, is H2O. And if I know the mass of something and I know its chemical formula, I can figure out how many moles I have. All right, and if I know how many moles I have, I can multiply that by the enthalpy, and that will give me kilojoules. So that's the process I want to do. I'm going to take that mass, 1.5 kilograms of water, times the molar mass, or divided by the molar mass. 1 mole of water is 18.0 grams. And oops, I see a mismatch here. Let's erase this. So my kilograms and grams are not going to cancel out because they're different units. So first, I'm going to convert these kilograms into grams. There's 1,000 grams in 1 kilogram. So now my kilograms cancel out. And now I can do the molar mass. And now I can use the enthalpy, 43.46 kilojoules per mole. My grams cancel, my moles cancel. And my answer is just 2 sig figs, because 2 sig figs is given, 3.6 times 10 to the third kilojoules, or 3,600 kilojoules. Never forget your units. Okay, so if you have a mass or number of moles of a substance and you know its heat of vaporization, you can figure out how much energy is required. All right, so along with the vaporization, all right, every liquid has a boiling point, which is often in chemistry abbreviated as BP, not to be confused with blood pressure, which is what all the nursing students would say BP is indicates. All right, so BP in chemistry, the boiling point, is the temperature at which the liquid's vapor pressure equals external pressure. That is the definition. The normal boiling point is the boiling point at atmospheric pressure. So because the boiling point is dependent on external pressure, different external pressures result in different boiling points. So you may know the boiling point of water to be 100 degrees Celsius / 212 degrees Fahrenheit because most people live around sea level-ish, all right? But if you live at really high elevation, okay, at higher elevation, water actually boils at a lower temperature because as you go up in elevation, you go down in pressure. The pressure goes down because you have less atmosphere actually pushing down on you. So the normal boiling point is down here at sea level, where atmospheric pressure is 1 atmosphere. But as the atmospheric pressure goes down and altitude goes up, right, boiling pressure, or the boiling point actually goes down. So if you were hiking in Colorado and you hiked up the mountain there and needed to boil some water to make some soup, okay, it would probably boil a bit quicker because that water would start boiling at 90 degrees Celsius rather than 100 degrees Celsius. Your soup also wouldn't be quite as hot. Also, if you buy pasta and you cook pasta in Colorado, they often tell you to boil it a couple extra minutes because the water is not as hot. It doesn't cook quite as fast, so you got to boil it a little bit longer. Oops, I meant to delete this picture and redraw it in my notes, but I guess I was just trying to, in a very sloppy way, show that as pressure goes up, the boiling point goes up. So this line here that I'm drawing is the boiling point at different pressures. And so wherever you reach 1 atmosphere, whatever the boiling point is at 1 atmosphere of pressure, that is the normal boiling point. All right. But the key is that water, for example, does not have a boiling point. Its boiling point is dependent on the atmospheric pressure because boiling point is defined as when the liquid's vapor pressure actually equals the external pressure. That's when you start getting bubbles bubbling out, and the process of boiling. All right, the next state chain is melting, or in chemistry we call it fusion. Fusion is the same thing as melting, and melting is when we go from a solid to a liquid by adding heat. So it too is an endothermic process and has a positive enthalpy. The opposite of melting is freezing, going from liquid to solid, and that's going to be exothermic. Gives off heat, releases heat, has a negative delta H. All right, so we call the enthalpy of melting, we call it the heat of fusion. Remember, fusion and melting, same thing. And the melting point is the temperature at which the solid becomes liquid. So we can write equations for the melting and freezing of water, and we can write the heat of fusion, which is endothermic and has a positive delta H, and then the opposite reaction, freezing, has the same value but the opposite sign, so it's negative 6.01 kilojoules per mole. All right, and we could do math problems with that just like we did above for boiling. Another state change to know about is sublimation. Sublimation is the process of going from a solid directly to a gas. And this happens sometimes. So the heat of sublimation, if we go back to chapter whatever we did, thermochemistry, and we talk about Hess's law, if you have two equations that you add together to get a third equation, so in this equation, in these two equations, the liquids sort of cancel out. So when we add them together, we get solid going to gas. That is sublimation. So the enthalpy of sublimation is the sum of the enthalpies of these two reactions. So the heat of fusion plus the heat of vaporization is going to equal the heat of sublimation. So you could figure out the heat of sublimation for a substance if you were given the heat of fusion and heat of vaporization. So what we can do for substances is we can create these heating curves. So you can heat a substance. So you take it in the solid state. All right, let's say at 0 degrees. We'll start this at 0 degrees Celsius, okay? And so let's call this, we'll talk about it for water. So like if this is water, you have solid, at 0 degrees, it's solid, okay? Actually, let's make it even colder than that. I need to make that. So let's make it negative 20 degrees here, okay? So you can have ice that's negative 20 degrees, and you can have ice that's negative 10 degrees, and you can have ice that's negative 5 degrees, all the way up to ice that is 0 degrees Celsius, okay? But at 0 degrees Celsius, that is the melting point. And so the ice will actually stay, it'll start melting and turning to water, and it'll stay at 0 degrees Celsius until it's completely melted. That ice will stay at 0 degrees Celsius. It won't be warmer. The water around it could be warmer, but the ice itself will not be warmer than 0 degrees. And then once it's all water, it becomes a liquid. The liquid can gain heat, and its temperature can rise until it reaches 100 degrees Celsius. I'm assuming we're at 1 atmosphere here, where it will start boiling. Boiling water is 100 degrees Celsius. You can't heat water on a stove to 200 degrees Celsius. It maxes out at 100 degrees Celsius. So there is something called superheating that we can chat about in class if you want. After that, once it becomes a gas, okay, steam, the temperature of steam can continue to rise. So that's why steam burns are particularly dangerous, because steam is actually hotter than hot water. So it can burn very quickly. So each of these different steps, I guess, in this heating curve involve a certain amount of heat. So if you have some amount of ice and it is melting, all right, then that's, you could figure out how much heat is being absorbed by that ice in order to melt it. How much heat do you need to melt a block of ice of such and such size? Okay, and you can also figure out how much heat you need to add to make a liquid go from one temperature to another, so from here to here. Okay, so when we are trying to calculate the substance at changing temperature but not state, so in other words, when we're trying to calculate something on one of these diagonals, so when it's a single state but it's changing temperature, all right, we're going to use the equation Q equals MCAT. Q equals mass times specific heat times the change in temperature. All right, and specific heat is usually given in joules per gram degree Celsius. So that means mass needs to be in grams and temperature needs to be in Celsius. If we want to figure out the amount of heat, calculate heat that's going on here as something is transitioning from one state to the next, but the temperature is staying the same, okay, then we are going to use this equation, heat equals moles times the heat of that state change. Okay, so for example, we can figure out how much heat is required to warm 10 grams of ice at negative 10 degrees Celsius to steam at 110 degrees Celsius. So in other words, we have a piece of ice down here that is negative 10 degrees Celsius, and we ultimately, this is my steam, okay, are going to heat it up to steam at 110 degrees Celsius, and we want to calculate how much heat it's going to take to do that. So we're going to do this in steps. So the first step is we need to figure out how much heat is absorbed by that block of ice as it warms up to melting temperature of 0 degrees. So the first thing we need to do is figure out how much heat the ice absorbs to go from negative 10 to 0 degrees Celsius. So we're going to use the QMCAT, the heat of that is absorbed is the mass times the specific heat times the change in temperature. I need some water. So the mass is 10 grams. The specific heat of substances is dependent on its state, so you can't just look up the specific heat of water. It's ice that we care about. So the specific heat of ice is 2.06 joules per gram degree Celsius. And you should keep this table handy. You'll need it. Times the change in temperature. So 0 minus 10 is positive 10. In other words, we've gone up 10 degrees. And so the heat here is 209 joules. All right, so that's just for this step here. That's 209 joules. Okay, so then the next thing we need to do is figure out how much heat does it absorb when it's melting. So step 2, we're going from, let's just say melting. And we're going to use this equation, moles times the heat of fusion. That's the state change that we're going through, melting. All right, so the moles, we're going to need to figure out from the mass. If we have 10 grams of water, and 1 mole of water is 18.0 grams, then that's 0.556 moles of water. So I can plug that in, and 0.556 moles times the heat of fusion, 6.01 kilojoules per mole, gives me 3.34 kilojoules. I do always appreciate it if you check my math on your own calculators, make sure that I am not in error. So I'll put that here. We've got 3.34 kilojoules. Now we're going to do this one, this step. I'm going to be scrolling back and forth a little bit here. So the third step is we're going from, we now have water at 0 degrees Celsius, and we're going to heat it up to the boiling point of 100 degrees Celsius. So Q equals MCAT. The mass is still 10 grams times the specific heat of water, liquid water, 4.18 joules per gram degree Celsius, times our change in temperature here, which happens to be 100 degrees. And we get 4,180 joules, or 4.18 kilojoules. So this part takes 4.18 kilojoules. Step 4 is the boiling, and we already know the number of moles because we calculated that in an earlier part of the problem. So it was 0.556 moles times the heat of vaporization this time, and that is 40.7 kilojoules per mole. Moles cancel out, and we get 22.63 kilojoules. So it's 22.63 kilojoules here. And then that last step, going from steam that's 100 degrees Celsius to 110 degrees Celsius. Q equals MCAT. The mass is still 10 grams. The specific heat of steam is 2.02 kilojoules, joules per gram degree Celsius. And our change in temperature here is simply 10 degrees. We're going up by 10 degrees. So that's 201 joules. Okay, so 201 joules. So in order to figure out how much heat to go from A to B here, we need to add all of these up. And that will tell us the total amount of heat. So step 1 was 209 joules. But we need some of these are in joules and some are in kilojoules. And we need all those units to match so we can add them all up. So I'm going to convert them all to kilojoules. So the first one, I'm going to convert that to kilojoules. So now I can add them all up. So we've got 0.209 kilojoules plus 3.34 kilojoules plus 4.18 kilojoules plus 22.63 kilojoules plus 0.201 kilojoules. Type it all in your calculator and you get 30.6 kilojoules, the total amount of heat necessary to go from a 10-gram block of ice to 10 grams of steam at 110 degrees Celsius, all right, is 30.6 kilojoules. The step that cost the most energy was this one, boiling. Boiling costs a lot of energy, and that's because water has a very high specific heat, and it has a very high heat of vaporization. Okay, so this is another one for you to try. A good idea is to pause the video here, work it, and then see if you can work out the same answer that I get. So I'm going to do this in a couple of steps. Calculate the heat released when freezing 5 grams of water. So we've got 5 grams of water, and we're turning it into ice. And this is at 65 degrees Celsius, and this is at -5 degrees Celsius. So the first thing I need to do is get my water down to freezing point. So go from 65 to 0 degrees. Q equals MCAT. So we have 5 grams times the specific heat of water, 4.184 joules per gram degrees Celsius, times our change in temperature here is -65. And so this is going to release, since it's exothermic, we get a negative value here, -1359 joules. All right, which just means it releases 1,359 joules of heat. Second step, We're going to calculate the heat that it takes to freeze the water to solid, from 0 degrees solid to 0 degrees liquid to 0 degrees solid of freezing. So, excuse me. I need to figure out how many moles that I have. So 5 grams divided by the molar mass of water. That will give me moles. So that's my N, times the heat of freezing, which is negative 6.01 kilojoules per mole. And this will also be a negative value, 1.669 kilojoules. And then the third step is taking that ice from 0 degrees Celsius down to negative 5 degrees Celsius. The mass is still 5 grams. The specific heat of ice is 2.09 joules per gram degree Celsius, and we are going down 5 degrees Celsius. So all of these are negative numbers. I'm going to add them all up. So if I add them all up, the sum is negative 3.08 kilojoules. And I should say that I need to convert these to match all. So this one's going to be kilojoules. To convert to kilojoules, I just divide by 1,000. So to convert this one to kilojoules, divide by 1,000, and now you're in kilojoules. Now I'll add them all up, and I get negative 3.08 kilojoules. In this question, it's saying calculate the heat released. This negative sign just means that's how much was released. So typically in a problem like this, you give the absolute answer. So the answer would just be 3.08 kilojoules of energy was released. The negative sign just means that it was released. Okay. So that's some thermochemistry, heat transfer during state changes. Again, of course, state changes, all that's happening in a state change really is it's using thermal energy to overcome intermolecular forces. So all substances exist in these different states. And for every substance, we can create something called a phase diagram. And a phase diagram plots the state based on it's a plot of pressure versus temperature, and shows you where different states, things exist at different states. So typically they look something like this. Okay, so in this zone here, where we have high pressure, all right, and low temperatures, this is where the solid exists. Okay, over down here at low pressures and increasing temperatures, this is where the gas phase exists. And then up here where we have somewhat high pressure and high temperature, this is where liquids exist, more or less. So phase diagrams generally have structures somewhat like this. So the solids will always be on the upper left, gases on the bottom right, and liquids somewhere in between. Some other anatomy of these phase diagrams. This point right here is called the triple point, okay? And the triple point is a magic coordinate, a magic pressure and temperature. It's not really magic, but I think it's kind of magical, where a substance can exist simultaneously in the solid, liquid, and gaseous state. So only at that one special temperature and pressure is where all three states can actually exist. This here, the end of this line, is called the critical point. And at that critical point, at this temperature and pressure, okay, any temperature or pressure above this, you sort of lose the difference between liquids and gases. So things become what's called a supercritical fluid. So it no longer has the properties of gas or liquid. It's something somewhere in between and funky. These lines here, right, these lines dividing the different states represent the temperature and pressure at which the state changes. So this line here tells us what the boiling point is. No, sorry, the melting point. So this is the melting / freezing transition. All right, so if you any dot on this, any given pressure, we can say what the melting point is, what the temperature of the melting point is. Same thing here, going from liquid to gas. All right, this tells us the evaporation and condensation temperature. So the boiling point, all right, any point on this line, depending on what pressure we're at, we can figure out what the boiling point temperature would be. And then likewise here, solid to gas, sublimation and deposition point along this line. Okay, so being able to read, I mean, the phase diagram, it's kind of like a map, or kind of like reading a graph with coordinates. So some of the things you should know, you should be able to sort of identify what's the pressure and temperature at the triple point, or at a certain pressure and temperature, is the substance going to be a solid, liquid, or a gas? So we're going to do a couple of practice problems on this page here. So they're a little bit poor resolution, but I have two phase diagrams. This one is for water, and this one is for carbon dioxide. And notice they're similar, yet different. Sorry. Okay, so they're similar in that the solid, liquid, and gas are, relatively same placement. One thing I want to draw your attention to is this line here. So there's a negative sloping line here on water, and a slightly positively sloping line here on carbon dioxide. And that is somewhat unique in water's phase diagram, that negative slope. And that's because water is a pretty unique substance in that its solid is actually less dense than the liquid, which is why ice floats. Most substances, the solid is more dense. The molecules pack more tightly together in the solid state, and so it's much more normal to see this positive sloping line, but not in the case of water. Water's pretty special. So we're going to use these phase diagrams to answer the following questions. Change up my marker color. All right, so the first one, A, B, and C, it wants to know what state are each of the following going to be at? Will water and carbon dioxide be at each of the following pressures and temperatures? So let's do A. At negative 30 degrees Celsius and 55 atmospheres. So I'm going to use my pen here on the water. Negative 30 degrees, it's probably somewhere like here, and 55 degrees or 55 atmospheres is maybe somewhere here. It's very much a guesstimate, but we're solidly in the solid zone for water. What about carbon dioxide? Negative 30 degrees is going to be, like right here, and 55 degrees is going to be like maybe right here. So for carbon dioxide, we're going to be pretty solidly in the liquid zone. So at that temperature and pressure, those two substances will be in totally different states. 25 degrees Celsius and 10 atmospheres. will be like maybe right here. So that's liquid for water. And for carbon dioxide, 25 degrees Celsius and 10 atmospheres will be like right here. So it will be a gas. And then lastly, -5 degrees Celsius and 1 atmosphere is still in the solid zone. For water, -5 degrees Celsius and 1 atmosphere is solidly in the gas phase for carbon dioxide. The phase diagram is also really cool because it shows us at 1 atmosphere, normal atmospheric pressure, if you have a piece of ice, of water that is frozen into ice, and you heat it up, right? It's going to first melt into a liquid, and then it will boil into a gas, right? It goes through 2 phase changes. But dry ice, which is made of solid carbon dioxide, if you have dry ice and you heat it up, it actually sublimes. It doesn't go through a liquid state. It turns directly into a gas. And this phase diagram really, it demonstrates, you can see that clearly on why dry ice sublimes. It's because at atmospheric pressure, liquid carbon dioxide doesn't exist. Okay. One more example question. What phase changes will water and carbon dioxide each undergo if the pressure is held at 1 atmosphere and the temperature changes from -10 to 10 degrees Celsius? That's basically what I just showed you. So for water, it'll go from solid to liquid to gas. So it will go through melting and vaporization, whereas for carbon dioxide, it's going to go from a solid to a gas directly. It'll sublime. It'll go through sublimation. So the last part of the chapter that I'm going to talk about is just an overview of the different types of solid materials. So we've talked a lot about different liquids and properties of liquids and boiling point. But I'm also going to just briefly talk about the different types of solid materials. So most solids are crystalline, form crystalline structures. There are several types of crystallines. So the first type are the ionic solids. So when you have an ionic compound, like let's say sodium chloride, any salt, any metal plus a non-metal, and you just have all these ions packed together, and they form this crystal structure. They're highly ordered, and what connects them and holds them together are ionic bonds or intramolecular forces. And ionic bonds are very strong, and so that means it requires a lot of energy to disrupt them. So salts tend to have very high melting points. Sodium chloride, table salt, will melt if you get it hot enough, but it has to be pretty darn hot. Metallic solids is the next type of solid material. And these are also highly ordered. This happens when you have a bunch of metal atoms together, whether they're the same metal atoms, like a bunch of gold atoms, or a mixture of different metals. Metals have their valence electrons are in the d orbital, which is, a little loosey-goosey. And so the valence electrons of a lot of metals can be shared very easily. So when you have a bunch of metal atoms, they kind of talk about metallic bonding as being a bunch of atoms in a sea of shared electrons. So electrons can flow very easily through metallic solids, which is why metals are good conductors of heat and good conductors of electricity, and why they can be magnetized, all right, because of their electrons. It's also why they are malleable and tensile, because the atoms can kind of roll because they're kind of held together by this sea of electrons. And so that's how metals, so metals are hard because those atoms can become densely packed, but they also can be separated in sheets. So you can cut metals to be very thin, and they can be shaped because these atoms can kind of flow more easily around each other without breaking, because again, they're kind of held together by that sea of electrons. As opposed to covalent network solids. All right, these are formed by nonmetal atoms when they get together, and they are held together by covalent bonds. Okay, covalent bonds are very strong, so these will have a high melting point because it takes a lot of energy to break those covalent bonds. And in fact, some covalent network solids are incredibly strong. Diamond is like the strongest material there is. Both of these materials are made out of carbon, just carbon atoms bonded together. So diamond is carbon molecules bonded like all four bonds apiece in this big crystal network, whereas graphite is carbon bonds bonded in sheets, flat sheets that then stack up on each other. So graphite, like think of graphite in your pencil. When you touch the graphite to a surface, a sheet or two, a couple of sheets or layers end up flaking off and leaving a trail on your paper. Covalent network solids tend to not be conductive, though graphite is actually a little conductive. You're going to actually use it as anode and cathode in your electrochemistry experiment later this semester. I don't remember what else I was going to say about these guys, but they're held together by covalent bonds, is something important to know. So there are solids like pure non-metal compound, like substances that are made out of pure carbon or pure silicon or pure sulfur, okay, are going to form covalent network solids. But there's not a ton of substances out there that are covalent network solids. A lot of metals form metallic solids, but a lot of the substances that are important in life, like water and carbon dioxide and iodine and sugar, like a lot of things, a lot of organic substances, and a lot of materials on planet Earth are actually molecules that are held together by intermolecular forces, London forces, or hydrogen bonding. And they just sometimes they form crystalline structures where they're highly ordered and the molecules pack together in a certain pattern. And sometimes not so much. Sometimes they're just kind of like randomly all thrown together. So these are called molecular solids. And so ice would be an example of a molecular solid. Water molecules being held together by hydrogen bonds. All right, so molecular solids have variable hardnesses depending on the types of attractive forces holding them together. Butter is a solid, but it's pretty soft because fat molecules, the triglycerides in the butter, are nonpolar. And so really what holds butter together as a solid is a bunch of London forces, and London forces aren't particularly strong. Whereas ice is a little bit harder because water molecules are hydrogen, it's actually a lot harder, are hydrogen bonded, which is a much stronger type of attraction. All right. Amorphous is just a term that we use when molecules are not in that highly ordered crystal structure, but in more of an amorphous or a randomly arranged group. So last section of the chapter, if you're reading in chapter 10, goes into detail of the geometry of crystal structures. And I'm skipping that, so I'm sorry if you wanted to learn about it. I think it's boring, so I'm skipping it. And I don't remember ever using it beyond general chemistry, and I took organic chemistry and biochemistry and never needed to use that. So hopefully you won't need to use it. And if you do, you'll learn it when that time comes. Or feel free to read ahead and do it anyway. The end. See you next time.